Structure and function of the muscular, respiratory, and cardiovascular systems by Andrew Fry, PhD, and CSCS.
So the superior part of the heart has the atriums, right and left, and the inferior part of the heart has the ventricles, right and left. Now there is a pathway through the heart, through a healthy heart, that the blood must flow. We notice that the blood starting from the right ventricle, blood that is returning to the heart is called venous blood. It's returning to the heart. It is deoxygenated, and it's coming primarily through the superior vena cava and the inferior vena cava. Comes into the right atria, goes through the right AV valve down into the right ventricle. This ventricle then helps pump the blood into my pulmonary arteries. Now, the pulmonary arteries send the blood to the right and left lungs, which are situated right next to the heart. It's very handy. So the blood goes either to the right lung or the left lung, drops off its carbon dioxide, picks up its oxygen. Now it needs to return back to the heart, only now it's going to go to the left side of the heart. Goes to the left atrium through my right and left pulmonary veins, and then it goes into my left ventricle. Now this left ventricle has to be very strong because now it gets pushed out into the rest of my system. It goes up through my ascending aorta, through the aortic arch, and then eventually down to my descending aorta, and it is now ready to go out through the periphery and start a whole nother cycle. Well, this heart, a unique characteristic of this heart is a muscle, but it is different from the type of muscle we've talked about a few minutes ago. This is cardiac muscle. It is not skeletal muscle, but it is a contractile tissue. It is designed to shorten, and thank heavens it's designed to shorten without high levels of fatigue. Your heart can just go and go and go. It also can be stimulated a little bit differently. The ability for my heart to contract is critical, obviously, because it's the contraction of the heart that squeezes the blood out of the chambers and pumps it out to wherever along the pathway it's going, whether it's going to the lungs, whether it's going out to the periphery, or whether it's just moving from one of the atriums into one of the ventricles. The SA node, or the sinoatrial node, is located at the superior portion of the heart, and it's almost, not exactly, it's over the right atrium, but it's situated close to both the right and left atriums. This is the primary pacemaker of the heart. It is what sets the pace for contraction, the SA node. And it sends a signal across through the myocardial muscle that surrounds the atriums. And then eventually that signal reaches the AV node, which is located right between the atriums and the ventricles, the AV node. At the AV node, there is a slight pause because the atria have to contract first, then followed by the ventricles. So at the AV node, there's a slight pause, and then the signal gets sent down through the septum, which is the myocardial tissue between the right and the left ventricles. And it goes down through the Purkinje system, Purkinje fibers, and it goes to the inferior portion of the ventricles, where then the heart muscle contracts, but it's contracting from the bottom up, so that the blood is now pushed up through either my pulmonary arteries or my ascending aorta. This pattern of stimulation is critical for the heart to pump the blood in an orderly and coordinated fashion. During diseases of the heart, signal transduction can be messed up, and you have problems with a properly functioning heart. Thus the role of a pacemaker, for example, to help correct that. Now, the autonomic nervous system is an involuntary system. It's sort of automatic, if you will. You don't have to think about this. Your heart is innervated by the autonomic nervous system. And there's two aspects of the autonomic nervous system. You have the sympathetic nervous system and the parasympathetic nervous system. And I like to think of these a little bit as the gas pedal in your car and the brake in your car. It's not quite as simple as that, but in this case, let's envision it as that. The sympathetic nervous system is like the gas pedal. It will increase the heart rate. The parasympathetic nervous system is a little bit like the brake pedal, and it will decrease the heart rate. and this will affect heart performance. Now, unlike driving, some people do, but you aren't supposed to have your foot on both pedals at the same time. But your body does. Your body always has a certain amount of sympathetic input, and it always has a certain amount of parasympathetic input. And the balance between these two systems is what helps determine how your heart functions. Let's also look about the signal that we can use to get an idea of how the heart is functioning. This is called the electrocardiogram, or the ECG. And this is just basically a signal of the electrical activity of the heart. We've talked about in skeletal muscle how an action potential comes down the neuron, crosses the neuromuscular junction in a chemical form, and then is reinstituted as an electrical signal across the muscle membrane. Well, in the heart, you've got a very strong electrical signal that, different from skeletal muscle, the electrical signal can pass from one cell to the next. It does not have to be sent through a neuromuscular junction. It can pass from cell to cell. That's a unique characteristic of myocardial muscle fibers. So the electrical signal is very strong because you have huge masses of myocardial muscle that are all contracting at the same time. So the electrical pattern is synchronized. What we see here is a rendition of what would probably be like a V5 lead if you were considering all the 12 leads on an ECG. Sometimes this is called the exercise lead because this shows some of the classic characteristics of the electrocardiogram. The P wave represents the depolarization of the atrium. The QRS complex, which is bigger, represents the depolarization that's just a little bit after the atrium, the depolarization of the ventricles. Larger muscle mass, bigger signal. And then finally, the T wave is representative of the repolarization of the ventricles. P wave, depolarization of atria. QRS, depolarization of ventricles. T wave, repolarization of the ventricles. So now you say, well, what happened to repolarization of the atria? That's actually hidden behind the QRS wave, which obliterates the repolarization of the atria. A lot can be determined from the ECG. A good cardiologist can find out an awful lot about your heart functioning from these signals. Now, let's talk about some factors that affect cardiac output. What is cardiac output? Cardiac output is the amount of blood that is expelled by the heart or pumped out by the heart in 1 minute. And cardiac output, which is in this case referred to as CO for cardiac output, sometimes you see Q with a dot over it, that also refers to cardiac output. This is determined from the equation heart rate times stroke volume. Heart rate is how often the heart is beating, how many times it contracts. Stroke volume is actually how much blood is pumped out in milliliters each time the heart contracts. So heart rate times stroke volume, how many times is it contracting, times how much blood is ejected on each stroke or each pump of the heart. And if I look at that for a time period of a minute, that is my cardiac output. Obviously, cardiac output is critical to performance in a lot of different activities. Several things contribute to cardiac output. Across the top of this figure, we see it's heart rate times stroke volume equals cardiac output, like we just said. Well, a number of things contribute to this. Stroke volume is dependent on several things. One is blood that returns to the heart helps to fill the chambers of the heart. This occurs between each beat. The time period between each beat is called diastole. So at the end of that period between each beat, when the heart is relaxed, it is filling with blood, and the amount of blood that is in the chambers is called my end diastolic volume. So how much blood actually gets into the chambers at the end of relaxation or the end of diastole. If I have more blood in there, then that means I can pump out more blood. I also have the factors that influence how strong a contraction my heart will make. Part of this is under sympathetic nerve regulation. Increased sympathetic activity increases the contractility of the heart muscle, makes it contract more forcefully. If I contract more forcefully, that means there's a faster and stronger ejection of the blood, which means I'm getting more blood out. which means I'm getting a smaller end systolic volume, how much blood is left at the end of the muscle contraction. I also have a concept called the Frank-Starling principle, and this is Frank-Starling. At one time I thought Frank Starling was a person. It's actually two individuals. But this is really a modification of the stretch shortening cycle that you see in skeletal muscle. As the chambers are filled with blood, they are stretched. The muscle, the cardiac muscle fibers are stretched. And as they are stretched, that gives them a greater capability for contraction. And so now, not only does sympathetic activity help the muscle to contract, but the stretch puts it at an optimal length and increases the strength of contraction. So if I can increase my end diastolic volume, and I can increase the strength of contraction to squeeze or pump more blood out, then I get a higher stroke volume. Now, my parasympathetic nerve activity is going to decrease my heart rate, and as a result, that will decrease my cardiac output. If I look outside the heart, the pressure that the heart has to work against, and we'll call this the mean arterial pressure, that is something that the heart is fighting against. High arterial pressures provide a resistance to the heart, and it has to work against that. Low arterial pressures make it easier for the heart. That's one reason why the problem of chronic high blood pressure, like in many disease states and low levels of fitness, can be a problem for the heart, because the heart has to continuously work against a high resistance in the periphery. A high resistance means there's less stroke volume, so this can affect cardiac output as well. And of course, we know during exercise, mean arterial pressure is changed, which affects cardiac output as well. If I'm looking at both aerobic exercise and resistance exercise, let's talk a little bit about blood pressure. Now, we'll revisit a couple terms. Systolic or systole refers to when the heart is contracting. So systolic blood pressure is the pressure that's in the arteries during the actual contraction of the heart, whereas diastolic blood pressure is a pressure that occurs during diastole between beats. Now, we see with the top left portion of the figure, we see blood pressure response to an endurance type of activity. And on the left, we see resting levels. On the right, we see maximum activity. Systolic blood pressure will increase as exercise intensity increases. However, diastolic blood pressure tends to stay about the same. It may change a little bit, but it tends to stay about the same. The body is moving continuously. You get a lot of muscle pump, if you will. You get a lot of movement of the peripheral limbs. This all helps to pump the blood. The mean blood pressure, which is a third the distance from diastolic to systolic blood pressure, will increase accordingly. Now, another thing to consider is the peripheral resistance. On the bottom left, we see from resting to maximum levels of exercise, we see that the peripheral resistance decreases during aerobic exercise. Why would this decrease? One, capillary beds are opening up. Unused capillary beds at rest become open. It means more space for the blood to go into. We see the muscle pump from moving limbs. This all contributes to a decrease in peripheral resistance. And therefore, the diastolic blood pressure is able to stay about where it normally is at rest. Let's look at a different scenario, resistance exercise. Top right figure is what occurs as you go from rest to high intensity resistance exercise. Now remember, resistance exercise, even if you're doing multiple reps, requires massive contraction of the muscles. And when muscles contract, they can actually squeeze off the circulation or occlude circulation through a muscle bed, if you will. And even though it's brief, it does occur. So one, we see an increase in the systolic blood pressure, but we also see an increase in diastolic blood pressure, which is because momentarily, as the muscles contract, blood may not be flowing through certain areas. The nice thing about this is it's very short-lived. I stop the repetition or I stop the set and I go back and that diastolic blood pressure goes down. This is unlike disease conditions where that may stay elevated for extended periods of time. Now the peripheral resistance is going to vary. How much resistance is out there is going to depend on the muscle mass. The more muscle mass I'm activating, the more occlusion is going on, which means there's more peripheral resistance. A Valsalva is when you forcefully hold your breath. and that means I'm increasing the pressure in my thorax, which means it makes it harder for venous blood to return to the heart, and that causes a backup in the system, if you will, and you get an increased peripheral resistance. The relative intensity is going to be, am I working at 50% of my one repetition maximum, or am I working at 90%, which is going to influence muscle mass, which probably will influence my Valsalva, but it all can influence peripheral resistance. So there's not a line that can be representative of what goes on during resistance exercise. Again, don't look at these lines and say, wow, I should stay away from resistance exercise because some of these blood pressure responses look like a chronic disease condition. This is very transient and stops upon cessation of exercise when it begins to return back towards resting. Obviously, if you're dealing with a disease clientele, you have other considerations to keep in mind. But this is due to the stress of the temporary exercise. So where is the blood going? Let's look at rest. We see where blood is typically pumped. And at rest, an awful lot of blood, a high percentage of the blood, goes to the heart or the gastrointestinal tract, liver, kidneys, and other tissues around the body. The skin gets a little bit. The brain always gets its share. Obviously, the heart gets its share. But skeletal muscle, if you're at rest, you're not doing very much. And most of your muscle is just quiescent, if you will. It's not doing very much. As I'm going to high levels of activity, though, a couple things I want you to note. One, the heart will always get its share. It's first in line, if you will. The brain always gets its share. However, you're pumping more blood during intense exercise. Your cardiac output has dramatically increased, so the total percent that's going to the brain is actually decreased, even though it still gets what it needs. Two things I want to point out, though. Huge increase in the amount of blood that goes to the working muscle, which makes sense. That is the tissue that is actually doing the work, that requires delivery of oxygen, that requires removal of carbon dioxide and other metabolites. It gets the lion's share. Also note, though, that the skin, the amount of blood going to the skin increases, both absolutely and relatively, a higher percentages as well. And this is because the blood flow is an extremely effective mechanism for dealing with the increased temperatures that come with exercise. My working muscle develops force, and a byproduct is an increased temperature. And we all know that we get warm and hot when we exercise. I need to get that heat from the inside of my body, from my core, to the surface of my body so that sweat can be evaporated, so that conduction and convection can deal with the heat, and the blood is a primary way of dealing with this, so the skin gets quite a bit. And all of these can be affected by training as you more effectively send blood to where it needs to go. Let's talk about an important equation. We'll spend a few minutes here looking at this, the Fick equation. Because if we're delivering blood to the working muscle, we're doing that so that oxygen can be delivered to the muscle, and primarily so carbon dioxide can be removed, as well as other factors. VO2, we mentioned, is the oxygen uptake. How much oxygen is being, or the volume of oxygen that's being delivered and taken up by the muscle in a given period of time. This equation basically is defined by the cardiac output, Q dot, times the AVO2 difference. A stands for arterial, V for venous. So the AVO2 difference is the difference in the amount of the arterial oxygen versus the amount of oxygen in the venous blood. So how much oxygen is in the blood being delivered to the muscle? How much is there after it's leaving the muscle? How much has been removed? So one, cardiac output is how much blood is being delivered, and two, out of that blood, how much of the oxygen is actually being delivered. And that is my oxygen uptake. Well, we can look at this equation in a number of different ways. If I look at oxygen uptake, VO2, as we said, that's cardiac output times the oxygen extraction, how much oxygen is being taken out. Let's define it as we have as cardiac output times AVO2 difference. But now let's replace cardiac output with the definition of cardiac output, stroke volume times heart rate. So I see that stroke volume times heart rate times the oxygen extraction, or the AVO2 difference, is also oxygen uptake. Well, I can take that a step further because stroke volume is the difference from my end diastolic volume, after my chambers have filled up during diastole, and my end systolic volume, after my heart has contracted and squeezed out as much. That's my stroke volume. It's squeezed out as much blood or pumped out as much as it can in that stroke. So oxygen uptake can be defined by end diastolic volume minus end systolic volume, multiplied times heart rate, that's cardiac output, multiply that times oxygen extraction, or the AVO2 difference. So remember, again, this can get confusing, but let's remember, VO2 is the oxygen uptake rate, and this is in liters per minute. So how many liters of oxygen you can actually take up in 1 minute. Cardiac output is also in liters per minute. How many liters of blood are pumped out in 1 minute? The AVO2 difference is arterial oxygen content minus venous oxygen content, and that's measured in milliliters of oxygen per 100 milliliters of blood. And then my stroke volume is the amount of blood ejected every heartbeat, and that's measured in milliliters per beat. So again, we see the three different ways to express that equation on the left, but those are the definitions and the units of measure of each of those variables on the right. My heart rate is expressed in beats per minute, a very commonly used and well-recognized unit of measure. My end diastolic volume, remember, is the blood in the left ventricle after it's filled up during relaxation. This is measured in milliliters. And again, my end systolic volume is also measured in milliliters. After contraction, what is left. So this is a nice way of describing exactly what is meant by VO2. Okay, so let's think now about the implications of the Fick equation. This is a nice equation for summarizing what's going on as far as the oxygen uptake is concerned. If I increase the end diastolic volume, which is the amount in the chambers after relaxation or between heartbeats, how much can they be filled? Or if I increase the heart rate, which I do during exercise, or if I increase the amount of oxygen that can be removed from the arterial blood, or the AVO2 difference. Any three of those increases combined possibly with a decrease in end systolic volume, which is the amount of blood left in the chamber at the end of systole or after the contraction. Any or all of these would increase my oxygen uptake, or my VO2. If I look at my end diastolic volume, and I combine that possibly with a decrease in end systolic volume, so an increase in end diastolic volume, the amount in the chambers after during relaxation, or a decrease in the amount of blood that's left in the chambers, this would increase my stroke volume, and again impact my VO2. Finally, if I increase my stroke volume in combination possibly with heart rate increases, this would increase my cardiac output, and that of course would also have a positive impact on my oxygen uptake, or my VO2. Well, let's talk about actually transporting oxygen. We've talked about getting oxygen from the lungs or from the external air, environmental air, into the lungs through the alveolar space, into the circulation. And now I need to get it into the blood. So at the bottom of this figure, I see my alveolus in the lungs, and I've got oxygen that is moving into the circulation. Now, a small amount of oxygen is dissolved in the fluid, but that's a very small, just measured in a percent or two. Most of it is bound to hemoglobin. Hemoglobin loves to bind oxygen. The only other thing that hemoglobin likes to bind is carbon monoxide, like you get in auto exhaust. If you're going out for a run and you're following the city bus down the street, that's a bad place to be. You're getting a lung full of carbon monoxide, and the hemoglobin will bind to that instead of oxygen. That's not where you want to be when you're trying to deliver oxygen to the working muscle. But under normal conditions, oxygen binds to hemoglobin, and now it gets delivered to the target tissue, and it goes down its pressure gradient and gets to, in this case, the muscle. Well, now I also have the exchange at the muscle of CO2. That's a metabolic byproduct. It goes down its pressure gradient. A little bit is dissolved in the fluid. Some of it binds to hemoglobin, because that hemoglobin is now empty. It's delivered its oxygen, and some of it says, hey, I need something to carry. Well, carbon dioxide can bind to hemoglobin. It's called carbaminohemoglobin. It prefers oxygen, but it's like a truck, a semi-truck on the highway. If you're a driver of a semi-truck, you hate to be driving an empty truck. You go from city A to city B and you take a load. Well, you hate to go back to where you started with an empty load. You like to load up with something. Hemoglobin is the same way. Now it takes the carbon dioxide back to the lungs. Some of it is also buffered through the bicarbonate system, and that only works for carbon dioxide. So the buffering system is effective, and once it gets back to the lungs, now the carbon dioxide can be moved down its pressure gradient and go into the alveolus of the lungs for expiration. So I'm able to transport both oxygen and carbon dioxide in my system. Let's talk about the ability to unload the ability to unload oxygen at the target tissue. This is the oxygen dissociation curve. And we see across the bottom of this graph the pressure of the oxygen in solution. And this is the unit of measure we've talked about earlier, millimeters of mercury, from 0 completely on the left all the way to maximum, or up to 100 millimeters of mercury, which is about as high as it goes in the typical person. I also see on the vertical axis how much oxygen, how much of the potential binding of oxygen there is from 0% up to maximum binding. Now I've got two lines. I have an untrained dotted line and I have a solid line, which is a trained individual. If you go all the way to the right side, and remember when we saw our diagram of the pressure gradients in the lungs and at the working tissue, remember that in the lungs, as the oxygenated blood leaves the lungs, it is at about 100 millimeters of mercury. And the right arrow points to that point. There might be a slight difference between an untrained person, but there's not very much of a difference. Most people can pretty much load up their hemoglobin with oxygen in the lungs. Now, as you move down the pressure gradient, the left arrow shows to what is often found in the muscle, about, say, in this case, 40 millimeters of mercury. If it was a highly working muscle, that may be even a lower percentage. At that point, how much of the blood can be, how much of the oxygen can be unloaded? And the difference between where the red arrow is pointing to on the right and the arrow on the left is pointing to is how much of all that oxygen that's pumping around gets dumped off at the working muscle. It's at that point that you see a huge difference between the untrained person and the trained person. So the trained person is able to unload more oxygen, thus their VO2 is higher. If I'm working even harder and that partial pressure is even lower, the difference becomes even more dramatic. And you can see why an untrained person is not able to work at those high intensities. What training does is it moves this curve to the right. By moving the curve to the right, that means I'm able to unload oxygen more effectively. And this is affected by several things. One is the temperature. The higher temperatures mean I can unload oxygen more effectively at the muscle. And we see this on the inset diagram, the top one. Higher temperatures, more effective unloading of oxygen. This is one reason you want to warm up before you exercise. I'm more effectively able to unload the oxygen. If I also change the pH or the acidic environment, lower pHs mean I more effectively unload oxygen, the curve moves to the right. And again, that might be part of warming up. That's a metabolic response, tells your body, hey, I'm working hard, my pH is decreased some, let's get some more oxygen to the working muscle. There are other metabolic byproducts that affect this as well. And as you might expect, if you're working at altitude, that has a huge impact because you cannot maximally load oxygen depending on how high in altitude you are because the atmospheric pressures become lower. It also points out that if you're doing anaerobic activities, the need for an oxygen mask, sometimes you see maybe a football player on the sidelines with an oxygen mask on their face. They're doing a highly anaerobic activity, and also they're very in shape and they are able to load their oxygen very effectively like you would see at the right part of the curve. So it basically has little to no impact on their ability to recover because of the characteristics shown by this oxygen dissociation curve. Let's talk about a very critical aspect of conditioning called the anaerobic threshold. Now, the anaerobic threshold, as we're going to talk about it today, is what's also called the onset of blood lactate accumulation. At what point do you develop enough lactate in your blood that you are no longer able to completely buffer it and maintain low levels? Resting levels of lactate are about 1 millimole. Now this diagram here shows a highly trained person who's running at a pretty good speed, 13, 14, 15, 16 kilometers per hour, and the lactates are staying fairly low. It's got a little bit of lactate, but not much. There's 2 points. One is sometimes called the lactate threshold, where you begin to get a little bit of accumulation of lactate, but more commonly used is the term anaerobic threshold, which is associated with about 4 millimoles of lactate, and we see that by the solid red arrow, and that is a point of deflection where that curve begins to increase curvilinearly. And it is at this point where you get a significant contribution from the anaerobic energy systems to the energy needs. This is the point at which lactate begins to accumulate, and this is what is often referred to the anaerobic threshold. Sometimes you hear people talking, giving a client a recommendation or an untrained athlete who asks, how fast should I jog or run? They'll say, well, today maybe you just run at a pace where you can maintain a conversation. Because we'll see in a minute, once you pass anaerobic threshold, your ventilation rate increases. And we'll talk about that in a moment. And if I'm breathing too heavy, I can't carry on a conversation, that means I'm probably past my anaerobic threshold. As soon as I move past my anaerobic threshold, that means my time to exhaustion comes a lot quicker. I can work a lot longer if I'm below my anaerobic threshold. In the sports setting, though, you may not have a choice. You have to work above anaerobic threshold many times, and so your training may have to be above that level, and it helps you to tolerate those higher levels of lactic acid. We see on the top diagram here, though, the ventilation rate. And the ventilation rate going from low levels of exercise intensity to higher levels also shows some break points. Now, a controversial area is, are these points where this curve changes because of the lactate response, or is it something else? But regardless, these deflection points occur at about the same point we see the deflection points on the lower curve, which is our lactate response. We see the lactate threshold and we see our anaerobic threshold, the second curve. One is, as I'm producing more lactate and it is beginning to accumulate, I've got to buffer it and get rid of it, and one effective way is through exhaling it as I breathe out. That means in order to do that more effectively, I have to increase my ventilation rate. And so I see that my ventilation rate increases exponentially as I reach that anaerobic threshold. Sometimes this is really referred to as the ventilatory threshold if you're not measuring lactic acid, but it seems to occur at about the same time. The other thing I'll point out that is with training, you can shift that lactic acid curve to the right. You can work at higher intensities before you begin to accumulate lactic acid. And if I'm a competitive athlete, I like that because that means I don't have to worry about the fatigue implications with high levels of lactic acid until I'm working at a higher rate. So whether you're working above or below your anaerobic threshold can have implications on the type of exercise prescription and the type of performance an athlete might expect. So in summary, this covers the physiological systems that are important to contracting muscle and how a person adapts in a strength and conditioning program. A lot of it is very basic physiology, but it all has practical applications, whether you're an athletic coach, strength and conditioning coach, personal trainer working in a clinical setting. All of these physiological systems are trainable and are important to know about for an optimal training program.
This concludes structure and function of the muscular, respiratory, and cardiovascular systems presentation.